So you've probably noticed that we call this course Introduction to Climate Science, Climate Change and Climate Modeling, and already you have been kind of mixing climate change and climate science in terms of energy budgets, carbon theory and so on. Why is that a good idea or not? You can actually focus on pure climate science without saying anything about climate change, but it's not clear whether that's a good idea at this point, because we're already in the thick in the middle of climate change that's already happening, and everything is already being affected. So most of the people who are not doing mathematical, physical climate science or system science are trying to learn climate science mostly because of climate change, and then apply it for adaptation, mitigation, solutions and so on, or climate and health, etc. So it's okay to mix climate science and climate change. Plus I will have a more specific second section focused on climate change. So we will keep doing this, and it's okay to repeat some of the concepts. So if you are doing social science or health or agriculture or energy and want to worry about climate change, then obviously you want to have certain level of understanding of the basic processes, and especially in terms of interpreting data like this. For example, this is the annual mean temperature of sea surface and land. What does it mean, annual mean? It's just like what we said before, climatology. How do we go from weather to climate? You average over a certain number of years, no fixed definition, but obviously you have to go long enough, a decade or two or three, and this is such a average of mean surface temperature. And immediately you see, you expect low latitudes to be warmer with these red colors than high latitudes. In the high latitudes you expect snow and ice regions like Greenland and Antarctica to be the coldest, because they reflect a lot of the energy just directly because of albedo. And high latitudes are colder because we already talked about the fact that they receive less shortwave energy than they reflect back to space as long wave radiation. Land temperature contrast can be much sharper than ocean, because ocean is deeper, high heat capacity, warm slowly, cool slowly compared to land. Land also has lots of urbanization and other things which affect local temperature contrasts like this. Deserts versus forests versus other like Himalayan ranges here have a cold temperature at such a low latitude compared to other regions, and the Alps well, should be somewhere here, and so on. Okay, Siberian low, Siberian high, and the reflectivity from the snow, etc., and so on. Plus, even in the low latitudes, you see many contrasts. The land contrast here of the Rockies versus the more tropical southwest, southeast. Colder temperature at these latitudes than here. Sharper front here than here. Many of you probably know the Gulf Stream that brings heat into this region and creates some contrasts. Indian Ocean is warm compared to other tropical oceans. It's more like the Western Pacific and the Maritime Continent, whereas the Eastern Oceans in the Atlantic and Pacific have much colder temperatures by 7, 8, 9 degrees compared to the western parts, because of the upwelling that we will talk about, which means energy is being moved from energy surplus region to energy deficit regions by winds, by ocean circulation forced by the winds, by cyclones, hurricanes. So everybody is doing their work. So those kinds of details you should be able to explain based on your climate knowledge, even if you are not doing pure climate science. That's the main goal. So let's recap few of the things we already said in the previous chapters. We said we are far enough away from the sun that the energy coming in is basically in parallel rays, but because Earth is a sphere, we have contrasting areas exposed to the incoming energy. So we have more area being exposed for the energy here than here, which is a more direct projection to light, whereas when you have a curvature, you're going to receive less energy per unit area than here. So the distance it has to travel is not really that different, but the area facing the sun is very different. So that leads to polar latitudes receiving less energy from the sun per unit area than mid latitudes and the tropics, and this also results in snow and ice, which creates albedo and more of the energy going straight back to space than in these regions. So together you add up also the tilt and the seasonality. So we have two solstices. In the northern hemisphere you would call it summer and winter solstices, and the same in the southern hemisphere. And you have two equinoxes when the sun is vertical on the equator. And what happens during the June solstice, northern hemisphere is facing the sun, so the southern hemisphere is away, and beyond the polar circle there is no solar radiation being received, no light being received, as we will see. And we have summer in the northern hemisphere, which means the northern oceans are receiving energy from the sun and soaking it up, and so on and so forth. You come to the March equinox. Let's go this way. So equal number of day and light everywhere because the sun is right smack on the equator. So that's why it's called equinox, equal day, equal night. Then you get the December solstice, where the southern hemisphere is facing the sun, winter hemisphere is facing away from the sun. That's what the tilt gives you. So the perihelion and aphelion are slightly different now. During the December solstice, sun is slightly closer to the Earth is slightly closer to the sun than during the June solstice. So the summers in the northern hemispheres and the winter in the northern hemisphere are slightly milder because of this slight asymmetry, but equinoxes are here, and we can look at it more clearly here. So during the June solstice there is 24 hours of sunlight to the north of the polar circle, and there is 24 hours of darkness to the south of the southern polar circles, with various length of days over here. And you see that the equator always has 12 hours of day and night, because it remains basically at the same angle to the sun. In March equinox, equal day and night. Remember, Earth is rotating around its axis. So instead of moving the sun, we are moving the Earth here. So September equinox. So let's go from March to September. You have another equator, sun being vertical on the equator, equal number of hours in day and night everywhere. And in the December solstice now, the northern hemisphere is pointing away, so zero sunlight to the north of the polar circle in the north, and 24 hours of sunlight here. So this energy balance also has to be accounted. Quickly to repeat ourselves, the visible is getting down to the surface in these radiation, because it's totally absorbed in the UV and at longer wavelengths, or absorbed at various levels. Outgoing long wave is absorbed by the greenhouse gases in certain wavelengths, but there is an atmospheric window in certain wavelengths where infrared radiation can go straight to space, because there is very little greenhouse effect in those bands. And why does it matter? Because if you are flying a satellite and you want to measure things at the surface, like surface temperature, then you probably want to use these bands, because the satellite can see all the way to the surface, because nobody is obstructing the outgoing long wave in those bands. But we are here talking more about the energy. So we already talked about emitted terrestrial radiation being distributed this way, high at the low latitudes and low at the high latitudes. There is a little dip here which relates to deep convection, and those clouds creating very cold temperatures at the top, which reduces sigma T to the fourth, so OLR, or emitted radiation, whereas absorbed solar radiation is minimum at high latitudes with an asymmetry because of the Antarctic versus Arctic, and land versus ocean distributions, and high at in the deep lower latitudes. Again, minimum over here because of the clouds, and this gives us surplus energy in the lower latitudes and deficit energy here. If we didn't move this energy, tropics would get warmer and warmer and warmer, and poles would get colder and colder and colder. That doesn't happen, so we are moving energy from energy surplus regions to energy deficit regions constantly, which is being done by atmospheric circulation and winds and so on, hurricanes, cyclones, and winds are then forcing the ocean, and ocean is doing its part in moving energy from the surplus region to the deficit regions as well. We can take these differences and infer how much energy has to be moved constantly, and we will see who does the work. It will turn out that ocean is doing most of the work in low latitudes in moving energy towards the poles, and atmosphere does most of the work in mid latitudes to move energy from the low latitudes to the polar latitudes. This is what gives us weather and climate, right? So this is what the background is. So we'll come back and look at a few more details as we go along. Mostly a recap, but it's good to hear these ideas again and again in different ways so that they get really fixed in your head properly. Okay.